Okay, this is a review video for the Chem 2 test that is tomorrow, September 11th, 2017. I'm really just going to go over the things where I think that you are probably having the most difficulty kind of sussing out as to what you're going to do when. And I think that's mainly with the stoichiometry. I think you guys are probably pretty good with the naming and the basic concepts, or if you're not, then well, you have a book that you can go read. But let me go through some of the stoichiometry in order to help you out with that. First of all, the mole, I know we deal with it a lot, but it's almost kind of like divided. We use it in two different ways. We use it in the case of trying to find formulas. And formulas are, that's a relationship in a compound, in an individual compound. And then we use it also to compare the relationships between reactants and products and how much are being made or how much we have to put into it with that. That's kind of more the cookbook chemistry part of it. I'm going to start with just mainly the mole as it is. You guys know that 6.02 times 10 to the 23rd particles, formula, molecules, whatever's in 1 mole. I'm not going to get into that right now just because it's not what we're really using in the lab. You guys can study and do those conversions on your own. But on this, the mole is also, will tell you directly how to find an empirical formula. Of course, the empirical formula is the simplest ratio of a particular compound. In H2O, water, you know that you have 2 hydrogens for every oxygen. When we build the models, it's, it's 1 red one and 2 yellow ones. However, this is also, when you multiply that entire thing by a factor of 6.02 times 10 to the 23rd, it's also 2 moles of hydrogen for every 1 mole of hydrogen. That's just how it goes. So you can call this as a mole ratio. It's a 2 mole to 1 mole ratio. So you can go opposite of that. Let's say you're given grams of a compound, of each element in the compound. Then you can go back and find the empirical formula. So I've got a question for you guys like that to work on. So let me put this up. And I'll let you guys write it down. Pause it, write it down, and then come back to me. Oh, and you have all your molar masses ready to go. Okay. Okay, to start working on this one, so we're trying to find the empirical formula. Simplest mole ratio. Well, are we given moles? Nope. So how do we go from grams to moles? This should be automatic in your head. Grams to moles is what? Divide by the molar mass. I'm not going to go through the proportion. I'm not going to go through the dimensional analysis of this because it should be that I'm automatic by now. You guys should know that. Grams to moles divide by the molar mass. If you don't, get there by tomorrow. So let's just go ahead and do this one then for 442. I'm not even going to write it out because these are things that you should, with your periodic table. It's 24.31 and you have 4.42 grams of it. So we have 4.42 grams divided by 24.31. Again, divide by the molar mass to get to moles. And we end up with 0.8 moles of magnesium in this compound. Okay. Now, how much chlorine is in this compound? Well, again, it's given us grams. And so we need to figure out how much chlorine is in it. So again, same thing. 12.89 divided by 35.45. And now a lot of the question is, okay, oh, wait, Mrs. Cox, it's H7. What do we do? Why don't we do by 70.9? Well, this is a compound, right? A compound is, they have exchanged electrons in a very intimate fashion. And so the chlorine isn't all by itself. That's the only time you have that is when chlorine's sitting all by itself in its own compound because it's so reactive. In this case, we are trying to figure out how many magnesiums and how many chlorines. So you just have to assume 1. That's why the molar mass is 35.45 and it's not 70.9. Just kind of basic conceptual between compounds and then chlorine as a diatomic on its own. Anyway, so we go ahead and do that and we end up getting 0.36 moles of chlorine. Okay, so let's look at this, our mole relationship. Well, how much bigger is 0.36? moles of chlorine to 0.18. Well, it's a 1 to 2, right? 1 to 2 ratio, 1 to 2. Now, if you can't figure that out in your head, then what you take the biggest one and divide it by the smallest one. And that comes out really, really, really close to 2. So you know that the empirical formula is MgCl2, which in this case is an ionic compound. How do you know it's an ionic compound? Well, magnesium is on the far left-hand side of the periodic table, and chlorine's on the far right-hand side. So that's just an automatic, so this is an empirical formula. You would never have a molecular formula for this because that's for something molecular, covalent, something like hydrogen peroxide, okay? That is a molecule. Well, molecular formula is not the simplest ratio. It's an expanded version of what the molecule actually looks like. So what would the empirical formula for this be? Ho. Okay, you guys always find that funny. Okay, so I threw that in there. So HO is the empirical formula to H2O2. So that would be the relationship. You have a question like that. Which one is which? Molecular formula is the real one. Empirical formula is one for is the simplest version. And again, molecular formula, you only have that for covalent compounds. You don't have that for ionic compounds because remember, they're always repeating a grid-like structure. So something like magnesium chloride is 1 magnesium and with 2 chlorines around it, and it's just repeated over and over and over and over in some sort of grid crystalline structure. Okay, so let's finish up that. I'm actually going to stop this video now, and then I'm going to post another one because otherwise I'm going to run over the 10 minutes. So go ahead. I'm going to do this, but let me give you the next problem that we're going to be working on so you can write it down. Go ahead and write that down so we can start working with it on the next video. Okay, see you in the next.